Today, we're tuning into a broadcast that you've been listening to your whole life, probably without even knowing it. We're going to eavesdrop on the secret electrical conversations happening inside your body every single second of every day. You've seen this a million times, right? In movies, on TV shows, that pulsing green line. But what is it really? Where does that signal even come from? And what is our body trying to tell us with it? Well, we're about to find out. Okay, here's how we're going to crack this code. First, we'll cover the basics, our body's electric language. Then we're going to tune our radio to a few different stations, the heart, the muscles, and even the brain. And to wrap it all up, we'll take a look at what the future of listening in might hold. Let's dive in. So, first question, how does our body even generate electricity? I mean, it's not like we've got little batteries or power plants inside of us. It all comes down to chemistry, really. It's the constant, incredibly fast movement of charged particles that creates tiny electrical sparks in our nerves, our muscles, and of course, our heart. This is what scientists call bioelectricity. And these signals, they are tiny. We're talking millivolts, sometimes even microvolts. So no, you can't charge your phone with it. It's better to think of it less like the power in your wall outlet and more like a massive, super complex system of Morse code. These little electrical pulses are the dots and dashes our cells use to talk to each other. Now, to understand that language, we've got to start with a single word. And in the world of bioelectricity, that fundamental word is something called the action potential. All right, let's zoom way in on a single nerve cell. Think of it like a tiny charged battery. Now, to stay charged, it does something really clever. It keeps a bunch of positively charged potassium particles inside. But outside the cell, there's an even bigger crowd of different positive particles, mostly sodium from the salt in your diet. This imbalance creates a kind of electrical tension, like a stretched rubber band, leaving the inside of the cell with a negative charge of about -70 millivolts. And this is where the magic happens, the spark. So the cell is just sitting there, resting at -70. Then a trigger comes along. It could be a thought, a touch, anything. That trigger opens tiny little gates in the cell wall, and bam! All that sodium that was waiting outside comes rushing in. This flood of positive particles instantly flips the cell's charge, all the way from -70 to +30. That sudden zap, that's the action potential. That's the signal. That is the word our body uses to send a message. So that's one tiny cell firing off one tiny word. How do we get from that to the famous heartbeat line we see on a monitor? Well, let's tune our radio to the loudest station in the body, the heart. An ECG, or electrocardiogram, isn't listening to just one cell. That would be like trying to listen to a single violin in a massive orchestra. No, the ECG is listening to the entire orchestra, all the heart cells firing together in perfect, coordinated rhythm. And what's so cool is that every single part of this waveform tells a story. See that first little bump, the P wave? That's the top chambers of your heart, the atria, getting the signal to squeeze. Then you get the big dramatic spike, the QRS complex. That's the main event, the powerful contraction of the lower chambers, the ventricles, pumping blood out to your whole body. And that final bump, the T wave, that's just the heart resetting itself for the very next beat. Doctors can read this just like a sheet of music. The heart's broadcast is constant, it's automatic. But other parts of our body only send signals when they have something to say. So let's check out two other stations that are more on demand, our muscles and our eyes. So we have electromyography, or EMG, which listens to your muscles. When you decide to flex your bicep, your brain sends a nerve signal telling it to contract. That's the signal an EMG picks up. And then there's electrooculography, or EOG. This one's actually pretty simple. It just measures the tiny electrical field of your eyeball as it looks left, right, up, and down. Okay, now for the most complex, the most mysterious broadcast of all, the brain. Listening to the brain isn't like listening to a single instrument or even a whole orchestra. It's more like trying to make sense of the noise from an entire city. This quote nails it perfectly. An EEG, or electroencephalogram, doesn't measure one single neuron firing. It can't. Instead, it measures the combined, summed-up activity of millions of neurons working together. It's like putting a microphone outside a giant stadium. You'll never hear what one person is saying, but you can absolutely hear the roar of the crowd when someone scores. The EEG is listening for that collective roar. And because we're just listening to that crowd noise, it's a really delicate process. The signal from the brain is 1,000 times weaker than the signal from the heart. That's why you need that cap full of electrodes and a ton of amplification, just to make sense of the brain's roar and find the important patterns within it. This table really puts it all into perspective.
You can see the heart, muscles, and eyes all broadcast in millivolts. They're relatively strong and easy to pick up. But look at the brain. Its signal is in microvolts. It's incredibly faint, which makes it by far the most complex signal to train and interpret.
Okay, so we're picking up all these raw, often messy signals from the body. How in the world do we turn that static and noise into clear, life-saving information? Well, that's where some seriously cool technology comes into play. Modern signal processing, and especially AI, acts like a super advanced radio receiver. First, it cleans up all the static. Then it identifies the key features, the important parts of the song. Finally, it uses powerful algorithms to analyze those patterns and translate the broadcast into something a doctor can use to make a diagnosis.
All of this leads to a pretty fascinating question. I mean, right now, we still need to stick physical electrodes on someone to listen in, but what does the future hold? Could the device in your pocket become your personal doctor? The real holy grail here isn't just making our sensors smaller and better. The ultimate goal is to move from wearables to non-contact sensors that can read our body's electrical language from a distance. The science is mind-bendingly complex, but the payoff could be revolutionary. Just imagine a future where your health is being monitored seamlessly, flagging problems before you even feel a single symptom. That's the future we're tuning into, a future where we can finally understand every last word our body is trying to tell us.